Thanks for having me. This is a joint paper with Alessandro Basurto, Philipp, Harting, Jasper, Hepp, and Dirk Kohlweyer. I think most of them are in the audience, if I'm not mistaken. So it has been done as part of the Growing Pro project, which we are involved in, and which now also has kind of a special COVID-19 work package. So the version of the paper I'm going to present today is kind of building on a paper we did previously. So we started to do this model. So it's agent-based model combining economic dynamics and virus transmission dynamics. Actually quite soon after the virus came up in March, and then we did first experiments. We did the first calibration. At that point, we were only using 6 weeks of German data to calibrate. By now, as you'll see, we are using actually 6 months. But in the end, our main results that we already got in this first paper, which we published well, as a working paper in June, kind of stay intact. But we have improved, we have added additional aspects, and I will come back to this. So this is a kind of a new version of that paper for those of you who know this paper, and it also, I think, has a few interesting new aspects compared to this original working paper. Okay, so I don't think I'm going to spend a lot of time to argue that it's important to understand how to fight a pandemic like the COVID-19 pandemic, which obviously has huge costs, both in terms of health costs, lives, but also in terms of GDP losses in all, more or less all over the world. So for Germany, actually now the official numbers are out, and GDP loss in Germany was about 5% in 2020 compared to 2019. Now, if we look at the different dynamics, both economically and with respect to the virus across different countries, we realize that there have been quite huge differences. And also we can see that different countries did have a little bit different approaches how to do containment policies and how to approach this problem to contain the virus and at the same time keep the economic costs as low as possible. So what we want to do here is to understand a little bit better what's the trade-off or the supposed trade-off that exists between keeping the virus down and reducing economic losses. And in the second part of the talk, I will also include kind of new developments, in particular the potential occurrence of mutations of the virus, but also effect of vaccinations. So the dynamics, so to speak, of vaccinations, as we can see now in many countries. Okay, so the main questions we want to address is how can we compare the different policies, so different types of lockdown policies, and we want to characterize those lockdown policies with respect to essentially 3 main parameters. One is the intensity of the lockdown. The second is the degree of opening after the lockdown. So obviously, if you have a lockdown and you open, you don't immediately open everything or not necessarily do so. And the third one is what is the time, or I should maybe say the incidence threshold that leads to a restart of the lockdown. So when do you go back into the lockdown once you have opened and you realize the numbers are maybe going up again? And so we want to characterize different policies with respect to those 3 parameters, and then we want to compare the effects of those policies essentially with respect to 2 key indicators. So one is the mortality of the virus once the whole pandemic is over. And the second is the economic loss that has been generated, and we'll measure this in terms of GDP. So we want to look at those indicators, but not only at the mean, but we also want to understand what is the ex-ante uncertainty. So more technically speaking, what is the variance of those losses, both with respect to mortality and the economic loss under the different policies. And we'll see that there are quite large differences also between this uncertainty that is associated with those different types of policies. Then, as I said, we'll look at the occurrence of more infectious mutations. And again, try to understand how can the different policies deal with that. And then we look at vaccination dynamics. So this is the agenda. Our approach, as has been mentioned, is we are using an agent-based approach to look at these questions. So what we do is we incorporate what you might call an agent-based version of a standard SIRD model into an agent-based macroeconomic framework. In particular, we'll use a kind of simplified version of the Euresid UniB model, which we have been using for quite a while now. So doing this, we will explicitly capture how the interactions that are necessary for economic activities, so in particular, meeting people at the workplace during production, but also meeting people at shops or meeting people while you're consuming services, how those economic activities act as virus transmission channels, and having an agent-based model, we can do it very explicitly. We will calibrate the model using German data, and then we will do a policy analysis where we vary those key parameters I've been mentioning, and then analyze the effect on mortality and GDP loss, both on the mean and the variance. Doing this, we can identify something which you might call an efficiency frontier. So different policies that seem to be efficient in a sense that if you want to get better with respect to one indicator, you have to accept that you get worse with respect to the other indicator. But we'll also identify policies that are actually inefficient, so that they are just above the frontier, meaning that you can essentially improve with respect to both indicators. And interestingly, we'll show that the policy that seems to resemble most closely what we have seen as a policy, for example, in Germany, seems to be not on the efficiency frontier. Okay, so that's our approach. The roadmap for the talk, I'm more or less done with the motivation. I will very briefly talk about literature, then I will introduce the model, talk a little bit about the calibration and the reproduction of the German data, and then present the policy analysis. Okay, so related literature, that's of course very tricky because I think by now there have been thousands of papers been written about COVID, all kind of different aspects of it. So here, let me just mention maybe a few approaches that are useful to show why we believe that our approach is new and also fruitful. So of course, there are many epidemic models. Some of them are just ODE models, so ordinary differential equations or difference equations. Then we have also stochastic difference equations, not so many, but also some. There have been simulation models for just transmission and the spreading of the virus, like older paper by Epstein, but also, of course, now newer ones. And those papers don't have any explicit economic aspect to them. But of course, by now there are also many what I would call eco-pandemic models. So economic models incorporating the virus transmission and dynamics. And there are different types of such models. There have been quite a few people interpreting this as a dynamic optimization problem. So you put like a standard seared type ODE into an optimization problem, and then you try to analyze what is the optimal policy. So this is typically done in a very simple framework. There are a little bit more complex frameworks. For example, this quite well-known Alessandro paper looking at age-structured populations. But what I want to point out is that these models actually, all of them, and I will mention one exception, work with very reduced form deterministic representation of the spreading of the virus. Similar statement is also true for the dynamic equilibrium models that we have seen. So I have cited a few here, which incorporate the virus into standard dynamic equilibrium, and then you can derive some, again, some statements about how to fight the virus and what are the, in this model framework, what are good measures to contain the virus. Those papers are much more reduced form, obviously, than our paper. They also, again, have deterministic virus dynamics, and they don't capture the interplay between the economic activities and the transmission of the virus in such an explicit form as we do, given that we really model in our framework the economic interactions explicitly, and therefore also the potential transmission of the virus through those meetings of different agents. So as far as I know, there is essentially one paper so far who is linking a stochastic model of the virus dynamics with some economic optimization problem, which is this one by Federico and Ferrari in the Journal of Mathematical Economics. So this is a little bit closer to what we do, but again, the focus is quite different, and also the stochastic dynamics is just a stochastic process, so it's much more reduced form. In the agent-based literature, there are now also a few COVID-related papers. I have already mentioned our earlier paper. There is a nice paper by Domenico and Severin Reisel, which is, I would say, closest to our paper, at least from the papers I have seen so far. Now, I don't think I have to go through the agent-based macroeconomics literature, because most probably you're all familiar with that. Let me just mention that, as I said, our economic part of the model is kind of based on the Eurosysony model. And here you can see a few references to papers written using this model, which has been used for quite a few different policy analysis in the past. Okay, so that's the very short literature part. Now let me briefly explain the model. Of course, agent-based models are always hard to explain in 10 to 15 minutes. So I will do my best, but of course it will be a little bit sketchy. So in the model, we have different types of agents. As usual in agent-based macro models, we have households, firms, and the government. The households here are age structured, so we have young and old households, which is important also because they, of course, react differently to the virus, and the fatality rates are quite different. So we have the young ones, they might work. So in principle, they are trying to work. They might be employed or unemployed. And in this model, we have different sectors. And each young household has some sector-specific skills. So this household can only work in a special sector. And the sectors we have are actually manufacturing, service, food, and public. I will come back to that in a minute. The old households don't work, so they are retired. They receive a pension, which is paid for by the government. And the fact that they're not working and the young are working also, of course, has implications for the spreading of the virus, because the virus can spread in the workplace only among young households, whereas old households can only get infected through other channels. The firms, as I said, are in 4 sectors: manufacturing, service, food, and public. Why do we have these different sectors? Well, first, those sectors are quite different with respect to the average number of people you are meeting when consuming the corresponding product. So typically, if you consume a service, you might think of going to a restaurant. The average number of people you are meeting is much larger compared to if you consume a manufacturing product. And so that seems to be important to be captured in a model like this, where the spreading of the virus is a very important aspect. So also, of course, productivity is quite different between manufacturing and service. And also, it's important to distinguish between those sectors, because in a lockdown, normally, and we have calibrated our lockdown measures, so to speak, to the German situation, you see a much more heavy reduction in activities in the service sector compared to the manufacturing sector. So we want to be able to capture that. Then we have the food sector. Food here stands for all essential products. So the food sector has two, I would say, important properties. One property is in a lockdown, the food sector is not reduced. So economic activity in the food sector is not reduced during the lockdown, as we'll see. And second, if the income of households goes down, the consumption budget for the food sector will be much less elastic to a decrease in the overall budget of the household compared to the other sectors. And finally, we have a public sector. So this public sector actually doesn't sell anything. This public sector is only hiring people. And the important role of the public sector in our model is that the public sector just continues hiring the same number of people. So the labor demand in the public sector is completely inelastic. And that's also important because we need it kind of to stabilize. And of course, it's also an empirical observation. That's what the public sector does. Okay, so labor is the only production factor in this model. So other than our original EUR/Z/B model, we don't have a capital goods sector here. We don't want to capture technological change or investment in capital goods because we're looking at a pretty short time horizon. So to keep the model as simple as possible, we have no capital goods. The sectors are heterogeneous with respect to different aspects. Some of them I mentioned. Another aspect is that the labor productivity is heterogeneous across firms, but also across sectors. So the productivity distribution is different across sectors, and it's taken from the data essentially. And then we have those firms competing. We assume there is something like price competition with differentiated goods. And in each sector, we have something which we call a sectoral mall. So for each of those three sectors where products are sold, which is manufacturing, service, and food, there is a mall. And all the firms in this sector offer the product at this mall. Consumers go to this mall and buy the product at this mall. And at this mall, they might also meet other consumers who are at the mall at the same time. Okay, so that's the basic structure. Then, of course, in order to get the model running, we need different behavioral rules of firms and households to make important decisions like pricing, quantity, choice, etc. for the firm, or also the choice between how much to save and how much to put in the consumption budget for the household, but also how to choose between different products if you see different products at the mall. So I'm not going to go into the details of this. These rules are essentially taken from the EUR/Z/B model, and also the calibration of these rules is essentially taken from the EUR/Z/B model. One aspect that's different, for example, from the Eurozidunibi model is that we have no wage heterogeneity within one sector. So wages are homogeneous in each sector, and the wages essentially depend on the average productivity in that sector. And then we have a government. The government, as I said, it's paying unemployment benefits, it's paying the pensions for the old ones, and is collecting taxes from the young working households and also from the firms. And the tax rate is adjusted just to try to balance the budget. And this will no longer be true if we are in a lockdown period. So then the government will stop trying to balance the budget. Okay, so here is a graphical representation of the model. I'm maybe not going to say too much about this. I think most of you know these type of models. So we have the firms who do some production planning, then they do production, then they deliver to the mall. We have a labor market where the firms hire and fire, the households search. We have the taxes being paid by the firms and by the households, and the pensions and unemployment benefits paid to the households. We have during the production the contacts at the workplace, and we have a goods market, which is, as I said, distributed over those sectoral malls, and there the goods are traded, and of course also there can be contacts at this mall. Additionally, there are social contacts. So those contacts are important because they drive the pandemic part, if you want, of the model. So in that respect, we have what you might call agent-based zeroed model. So each household can be in one of those 4 states: susceptible, which is the initial state for everyone, infected, recovered, or dead. And at each meeting, if an infectious meets a susceptible household, then the susceptible becomes infected with a given probability P-inf. So that's, of course, a very important parameter in the model which we will calibrate. Now, once you are infected as a household, there is a latency period, and after that, you become infectious for a certain number of days. Also, this one, of course, can be taken from the data. And then, if you're still alive, you recover after a certain number of days. But while you're infected, there is a hazard rate, or we might call it a fatality rate, that you die. So every day there is a certain probability that an infected household dies. And this fatality rate depends on the age. So as we know, it's much higher for old compared to young. And it also depends on the utilization of the available intensive care units. So this is also something we calibrate from the data. And if these intensive care units are overutilized, then the fatality rate grows, and it grows rather steeply. And this is not so easy to calibrate. We try to do it based on Italian data from the April of last year. Okay. Now here you can see again the transmission channels. So how can the virus be transmitted? Meaning at which points can agents meet? So first they can meet while they're working. So those agents, each agent, each young agent who is employed has an employer. So we know for which firm this agent is working. And at this firm, you might meet other people working for the same firm. And this generates a certain number of meetings at the firm. This also means that essentially the size structure of the firm is explicitly taken into account, and the size structure of the firms might also influence the diffusion dynamics of the virus in that way. Additionally, those agents might meet while they go shopping. So at the mall, the way this works is that every agent, young or old, for each sector has 1 day a week where this agent would go shopping if there is no lockdown. So these are randomly drawn days where they go shopping. And if you go shopping at a certain day to a certain sectoral mall, then you can meet people who are at this mall at the same day. Okay, and that again might be old or young agents. So this is how, again, people might meet and the virus might get transmitted. And additionally, there are just social contacts. So those are the green arrows here. So we have a kind of a very simplified representation of an age-structured social network where agents might meet people of their own age or of the different age group, and the probabilities that they do this, or that the average number of meetings they have with those different age groups is, as I'll say in a minute, taken from a British study actually. Okay, so this is the model. Very brief description of the model. If you have any crucial questions about the model, please ask them now. Otherwise, I will go on to describe the policy measures that we introduce into this model. So there is what we call individual prevention measures, which you might interpret as wearing masks, for example. And those individual prevention measures will reduce the infection probability from p-inf to 1 minus xi times p-inf. Xi is again an important parameter, and this tells us how effective those individual prevention measures are in reducing the infection probability at one single meeting. We will assume that during the containment policy, whether you're in lockdown or you are in the opening phase, their individual prevention measures will be in place. So there will be xi, but we will assume that xi is actually different between the lockdown and the opening. So we will have more severe individual prevention measures during the actual lockdown compared to the opening phase. Similar applies to the social distancing. So the number of social contacts, I just mentioned that we calibrate this based on normal kind of pre-virus data. And then we assume that during the lockdown, this number of social contacts is reduced. We also assume that during the whole containment policy, they will be working from home. So meaning whether you are in the lockdown phase or the opening phase, as long as the virus is active, so to speak, we will have working from home measures in place, meaning a certain fraction of employees for a firm will not come to the workplace and therefore will not meet people there. And the fraction of employees that can actually work from home is sector specific, and again will be calibrated from German data. Now the policy measure I will talk about essentially for the rest of the talk is the fourth one, which is the reduction in consumption activity. So as I said before, in normal times, each household once a week would go shopping at each sectoral mall. Now, if you have containment measures, then this weekly shopping probability is reduced from 1 to some probability PS, and this probability will depend on the sector. So it will be can be a sector-specific reduction in the probability that a household consumes from this particular sector, which also means that this household will not have any meetings with other people at malls for this particular sector. So this will be a crucial parameter, this PS for the different sectors, and I will come back to this in a minute, how we calibrate this. Additionally, we assume that there are economic support measures in place during the containment policy. In particular, two. One is short-time work. Short-time work means if a firm would like or would normally lay off a certain number of people because their production plan is going down, then not all of them become unemployed, but a certain fraction of those people that would normally be laid off are not laid off, but are moved to short-time work, which means essentially that they get a wage, a reduced wage, of course, but still they receive a positive wage, which is financed by public transfers. So that's the short-time work scheme. And then we have a bailout scheme in place, which we can also see in many countries. Of course, they're kind of a little different across countries. So we assume something very simple here, which is if during the containment policy being in place, the firm a firm gets the savings to be negative. So normally in our standard model, that would mean then that they would become insolvent and would have to stop, to essentially to leave the market. Here they don't, but those negative firm savings will be balanced by public transfers. So those firms will be bailed out and they will stay in the market. Okay, now here, as I said, the focus is on 4. Also, I should say 1 to 3 don't have any direct economic effects. 4, of course, has. I will, let me maybe say one more word to the economic support policies. I will not say much about this in the rest of the talk. In the previous paper that we were that we got out in June, we were actually looking at this, at comparing scenarios where the government is not doing such economic support policies. And we realized that actually having those economic support policies in place not only obviously reduces the economic losses associated with the containment policies, but also it actually does not negatively affect the public budget at the end of the period that we consider. So it's actually more costly not to do it, also in terms of public deficit that you're generating. Okay, now the calibration of the model, we use, as I said, for most parts, empirical data from Germany. So this covers the age structure that we implement, the sector-specific average firm productivities, the relative sizes of the sectors, also the fraction of employees that might work from home. We take from a German study. Where we don't take German data because we didn't find any, is this data on the social contacts. So here we rely on a, I would say, very interesting and useful study done by Mosson et al. In 2008, where they ask households in Britain to essentially keep a diary of how many people of different age they are meeting every day and at which places they're meeting them, whether they're meeting them just privately or at their workplace or shopping and so on. And so this is exactly more or less the data that we need, and we were using this data to calibrate our age-structured distribution of contacts. Then, of course, there is now a lot of data on the duration of the latency, the infection, also the age-specific fatality rates we took from kind of more or less standard COVID data, and the ICU capacity is again the ones for Germany. Of course, we assume that not every infected is actually detected. So we assume that essentially about 1/6 of the infected are actually detected. So there are different numbers on this for different countries. So 1/6 is maybe a relatively low number in that respect, but there have been yes, estimations or estimates between 1/4, but maybe also a bit lower than 1/6. So we don't believe that it's a very crucial aspect. So I guess what we find would be quite robust if we would change it a little bit. Okay, then we have this p-inf, so the standard probability of being infected if no measure whatsoever is in place. And so this p-inf we have calibrated in a way that if we implement no measures, we get an R0, which has the usual value that has been reported of something like 1.5. And then we have the effectiveness of the individual prevention measures, this xi. So as I said, actually there are two values of xi, one during lockdown and one during opening. And those two we have calibrated to match the German data. And I will show you in a minute that this match is actually quite nice. So before I show the match with the German data, let me mention that in the paper in June, we also looked at what's happening in our model if there are no containment measures in place, and then we see what you would expect. You see this kind of huge infection wave, which is very similar to what you see in other seared models. And you see very little economic effect. Of course, you do see a little bit of negative economic effects just because so many people are actually dying because of the virus. Okay, now we, as a first exercise, we have reproduced the German dynamics for 6 months from March till September. And you can see here the green data is actually the German data. The blue data is the mean of 20 runs with our model. And you can see the confidence bands here as the dotted lines. And you can see, okay, the reported total infected fits quite nicely. This is a smoothed R0, so it's smoothed over 1 week, otherwise it becomes too volatile. Is also fitting quite nicely to the German data. The casualties fit kind of. And what is also important, of course, is that not only the epidemic dynamics, but also the economic dynamics seems to fit quite nicely. So in particular, here we show the worker and short-time work. The blue one is our model. The green one, that's the monthly data that's published in Germany for the fraction of people in short-time work. So also this seems to fit quite well, and we have a few more of those. Okay, now given that that seems to establish that the model is quite a useful model to look both at the epidemic and economic dynamics, now we do our policy analysis. And for this, we define our lockdown measures. So as I said, we have 3 key policy parameters. We first have what we call the alpha L, which is the intensity of the lockdown. So if you introduce a lockdown, you reduce these consumption probabilities of the households, and the sector-specific reduction, if the alpha is just 1, is that it's 15% reduction for manufacturing and 50% for service. And as I said, nothing for food. Those numbers are calibrated in a way that if you put alpha equal to 1, you essentially get the effects of the German lockdown, so the first German lockdown last spring. Now, then at some point, if the numbers are sufficiently low, you might want to open up. And during the open up phase, then you have an alpha, which is called the alpha O. So clearly the alpha O should be smaller than the alpha L because you will reduce consumption less during the opening up. But the question is, how much do you open up? And then once you've opened up, numbers might go up again. And then you have this third parameter, which is the beta L. And the beta L has the interpretation that if the incidence, so that's the usual definition, the number of infected during 7 days for each group of 100,000 households. So if the incidence number is above this beta L, then you go back into the lockdown. So if I say number of infected, of course, I should say number of reported infected. Okay, so the default policy is again what we would at least in spring what we thought is the German policy, and so that's 1050. So during the lockdown you have an alpha of 1, then you open up, and you go back into the lockdown at an incidence of 50. I'm saying that we thought that that's the German policy because, as it turned out, the actual German policy was more like 100, or maybe even more than 100, because Germany went into lockdown when the incidence was even higher than 100. So in that sense, this is Germany had an even higher threshold than these 50 here. You could think about a fourth threshold, which is the threshold when you stop the lockdown. So this one we just fix here. So we put it to 5. So you really keep the lockdown for a long time. This is more or less what Germany did during the first lockdown. And we did try robustness. If you have a higher lockdown here to exit the lockdown, sorry, if you have a higher threshold to exit the lockdown, this doesn't change much. It's actually a little bit less effective if you do that. So in our default setting, we assume this is going on for 18 months. After 18 months, all of a sudden, everyone is vaccinated. So the infection probability goes to 0, and the lockdown policy is simply stopped. Since even after you stop the measures, there will still be some adjustment of the economy. We look at a time horizon of 24 months. So we also look into what's happening 6 months after the end of the measures. Okay, so this is now maybe the main figure. So what we do here is we define different policies. We start with the default policy, which is this policy A here. So remember, the default policy was 1050. So you have a relatively strong lockdown. You fully open up once the numbers are low, and then you wait till the incidence is 50 to reintroduce the lockdown. So that's A. So we run 20 runs for this policy A, and then we look at the mean of the mortality after the 24 months and the GDP loss after the 24 months. Well, the average GDP loss during the 24 months, that's what I should say. And then you get this point here. And now we vary those key parameters. So like if we follow the black line, what we do is we reduce the threshold at which you go back into the lockdown. And you see if you reduce the threshold of going back, this is essentially not reducing substantially the GDP loss. Actually, down here at point B, you have a threshold of 5 compared to 50 up here. And the average GDP loss is more or less the same, which is maybe a little bit surprising because you would think you have such a high threshold because you want to reduce the economic loss, but that's not true here. What is true is that by doing this, by having a much smaller threshold, you strongly reduce the mortality that you get. Now that's the black line. The red lines tell us what happens if you make the lockdown more severe, which is going to the right, or less severe, which is going to the left. So here, as I said, this is the standard lockdown that has been done in Germany. So here you only have 75% of this reduction in consumption activities. Here you have only 50%, you have only 25%. And this you can do here for a threshold of 50, but you can also do it for a threshold of 5. And you see this red line below between points B and C that kind of looks more like an efficiency frontier, so which is a very small threshold. If you make the lockdown lighter and lighter, you get a trade-off that you have lower economic losses, but you have higher mortality. However, another option is to still have a relatively high threshold, which is point A here, but then the blue line, and that's here the blue dotted line, means that when you open up, you don't fully open up, but you still keep some restrictions while you're opening up. So this again here is, this point is you open up keeping still 25% of the reductions that you had during the lockdown, and this point D is you keep 50%. So you keep kind of half the lockdown while you're opening up. And this point here also clearly dominates A. So what we can see is, okay, this point A, high threshold, and going back and forth between strong lockdown and full opening is really dominated by several points, in particular by this weak opening point, and also about those points C and E. So E is very similar to C, it's just that during the opening you don't open up fully again. So this point E essentially means you're just keeping constant light lockdown all the time. And those points here also seem to dominate A with respect to the mean, but as we'll see also with respect to the variance. Okay, I think I'm running a little bit late, so I'll have to speed up somehow. Now, if you want to understand why this is the case, so why is this policy A relatively ineffective, we can see it here from the dynamics. So here we see the dynamics of the total infected and the GDP under the different policies. And we can see under the benchmark policies, we get this wave. So we get a second wave, we get a second lockdown, and then we get kind of starting a third wave before the vaccination comes. And in terms of GDP losses, these waves, every time you introduce a relatively strict lockdown, this generates a lot of economic cost because firms lay off people. We have frictions in the model, so it takes time to get up again. And then here, if you have a second wave, you have a second kind of severe lockdown, you again go down. And this generates not only relatively high mortality, but also relatively high economic losses of this policy A. Now, if you look at the weak opening policy, which maybe is kind of the most attractive policy, you can see, well, you have the first wave, then you get the numbers down, but then because you do only the weak opening is just good enough to keep the R0 slightly below 1, or most probably approximately at 1, so you don't get a second wave. Doing this, you can see in the GDP, you have the initial lockdown. So also with this policy, you have initial large losses, but then when you recover, you stop the recovery at some point because you keep the reductions in economic activity during the opening because it's a weak opening. So you don't go back to the initial GDP level here, but you kind of go parallel here till the vaccine is here and you go up. But overall, this is just the dominating this policy A. And one additional aspect, and I think it's a relatively important aspect, is that this, if we now just concentrate again on A and D, that not only is the mortality much smaller with approximately the same GDP loss, but the variance, which is given here in brackets, is just way, way smaller. So with this policy D, you have a pretty clear idea what will be the outcome at the end of the 24 months. With this policy, you have much more variance. And this can be illustrated if you look at single runs. So here you can see single runs, just six randomly selected single runs under policy A. And you can see there's a huge variance. So this is structurally exactly the same economy. So it is, the difference between those curves is just pure random. So it's luck, whether you are in the red curve or you're in the black curve. Yes, this is also interesting, I think, if you look at the discussion that we have where countries are compared all the time. So this country now has much better numbers, so it must have been doing something much better than the other. So those countries are all doing exactly the same, and they are structurally exactly the same, and nevertheless, you get very different dynamics depending on the individual run. And this also, so this is for the infected, and because the infected dynamics, of course, drives the lockdowns, you see the same for the GDP. So also with respect to the GDP loss, you see this black line here, which is just having this very bad lockdown very late. And this is generating huge economic losses again compared to these other runs where this doesn't happen. So here you really, ex-ante, have not a very clear idea what will be the dynamics that you will see. And it's completely different if you do this weak opening policy. So here, essentially, if you look at the GDP graph, you have very little variance. So you have a much clearer idea what you are getting into if you have a policy like this. Okay, so this is without mutations. Now, I think I'm almost out of time. So let me just spend, do I have 5 minutes?
So we have 8 minutes left. So this includes the question time as well. So if you could wrap up.
Okay, so then I will do just 2 minutes. Okay, 2 minutes. So then I will not describe in detail what we're doing. So we are introducing now a mutation. So the mutation at some points, just some randomly chosen infected people mutate to a different virus. And from that point on, everyone who is infected by this person and by the persons infected by this person and so on has this other virus. And the new virus has a 1.5 times as high infection probability. So the main point here is if you have this, those policies C and E, which we're actually doing pretty well under our standard scenario now, don't do so well anymore. So if you have this continuous light lockdown, if this more infectious virus comes along, this is actually not working so well, so mortality goes up. Our weak opening policy still does much better than A, I would say. So let me just say this about the virus. And finally, we introduced vaccination. So we don't assume that everyone is vaccinated after 18 months, but we actually have a dynamics of vaccination. And what we can do now is try to understand for which percentage of vaccinated people should you stop all containment measures. And here we see what's happening for the different policies. So I don't have time to go into the details. But what this tells us essentially is in our model, between 25 and 40% is what you need to be able to stop the containment measures without really having a much significant negative effect on mortality. Okay, and also our general picture that we had qualitatively stays intact even if we have vaccination. So that's it. We have this agent-based model combining a macro model with a pandemic model. And the main policy advice I would derive from this is weak lockdown policies or weak opening policies seem to work much better in terms of means, but also in terms of uncertainty. And if you take into account that viruses may come along, then actually weak opening might even be the better choice than weak lockdowns. And as I said, our at this point, a little bit preliminary results, I would say, would suggest that you might stop these containment measures when you have between 25 and 40% of the population vaccinated. Thanks a lot. If you want to have a look at the model, it's available here on GitHub.